a mathematical function. A mathematical representation can be used to describe a situation happening in the nature. Here we have a mechanical setup. This is familiar to us, the simple pendulum, and this is the equilibrium position, undisturbed position, mean position of the bob. If it is displaced from the equilibrium position, x, that represents the position of the body at various instants of time. And since x is changing, the instantaneous displacement also will be changing with respect to the position of the body from the equilibrium position. Now if x is small, the angle made here also will be small, and the maximum value of x, that can be termed as the amplitude. If theta is the angle made here, omega can be used to represent angular velocity. Velocity is displacement by time. Here it is the angular displacement divided by time. So theta can be expressed as omega t. Now the nature of this displacement, we know at the equilibrium position, with respect to the equilibrium position, the displacement is 0. Then it increases to the maximum value, then comes back to the equilibrium point. Once again the displacement is 0 with respect to the equilibrium point. Second time it touches the equilibrium point, then going to the other extremity, and when it is coming back to the equilibrium point for the third time, one oscillation is completed. If it is starting from here, going to the other extremity and coming back to the equilibrium point, but it is not able to come to rest there, because in its return journey it has acquired momentum with which it is overshooting the equilibrium position. Amplitude is made in the opposite direction, and for the third time it comes back to the equilibrium position. One oscillation is completed. So the nature of the displacement, its variation, we know it varies between minimum value and the maximum value, and also the time required for one oscillation, if we are calculating within the same time interval, the same kind of motion will be repeated. So the displacement is in such a way that its value changes between 0 and the maximum value, minimum value and its maximum value within definite intervals of time. So to represent such a displacement, we need a function which is also varying between its minimum value and maximum value within definite intervals of time. We know if we are using this trigonometric function sine theta, suppose we know this is the graph of sine function, and this is time, and the displacement, suppose we are considering like this, maximum value of x is amplitude. If you are starting from here, see 0 with reference to the equilibrium point, and x increases to the maximum value, the displacement, and then it comes back to the 0, comes back to the equilibrium point. Second time it touched the equilibrium point, and going to the other extremity, so the amplitude in the opposite direction is made, and then it is coming back. So 3 times this value, 0 value for the displacement. So one oscillation is completed, and so the sine function can be used to represent the displacement, and the value, the x, that depends upon theta. Larger the displacement, greater will be theta, and the maximum value of x is amplitude. So x can be represented in terms of amplitude, a sine function of amplitude. Theta is equal to omega t. Now we know we are applying a force to displace the body. So the applied force can be expressed in terms of Newton's second law. F is equal to ma, Newton's second law of motion. Acceleration is the first differential of velocity. dv is small change in velocity, and it is the time interval over which, during which that change takes place. So velocity can be expressed as the first differential of displacement, small change in displacement, and the interval of time. So acceleration is equal to dv by dt, but v is equal to dx by dt. So d by dt of v is dx by dt. So acceleration is equal to the second differential of displacement, d square x by dt square. So Fa, that is applied force, m into a is equal to d square x by dt square. Now we know if we are releasing the body here, it is able to come back. It means that there is a force that helps the body to restore its equilibrium position. So that force is known as restoring force. A formulation of restoring force, it was first done by famous scientist Robert Hooke. So Hooke's law. So we know if you are displacing the body to greater displacement, for example, if here the bob or a block of mass m attached to a spring, if you are elongating to a displacement x, it will come back. But if the displacement made is greater, with greater force it will recoil back. It will restore its initial position. It is restoring its initial position with a greater force. So the restoring force F suffix r proportion to x, F is equal to kx, and this restoring force is opposite to the applied force. So we are attaching a negative sign because the applied force takes the body away from the mean position and the restoring force takes the body towards the mean position. So in magnitudes they are equal. Applied force is equal to restoring force, but the direction is opposite. Now we can equate it because it is able to come back to the same position. So applied force, it is equal to the restoring force. Restoring force and applied forces are equal, and the direction is opposite. This is Newton's second law of motion for applied force, and from Hooke's law we have restoring force. And bringing this to the side and dividing throughout by m will be cancelled here, and this will be cancelled. So whenever we are finding a second degree differential equation, d square x by dt square plus k by m into x equals 0. So it is nothing but a simple harmonic motion.